So in this unit, what we're looking at is um, how in a reaction sometimes we can create or we can create heat or we can lose heat. And so that's what we're looking at. And so the first thing we need to understand is the energy that's going on in a reaction. So energy, if you remember back, can have multiple forms. And so here's some examples. Okay. You can have radiant energy. That's the energy that's coming off of like the sun or a light bulb. It feels like heat. You have thermal energy, which is also heat, but it's more of the inside the reaction. You have chemical energy, you have nuclear energy, and you have electrical energy. Of course, there's more types, but those are the ones that we're going to look at, especially in chemical reactions. So first off, we have to understand that there's two main types of energy when we're talking about these reactions. Sometimes you're going to have energy that is due to motion. That's called kinetic energy, and it's going to be dependent on your mass and your velocity. In your notebook, we talk about a specific formula for that. Okay, so this bike rider, she has kinetic energy. She's moving. She's going up the hill. She's requiring some work to do that. She's putting energy in. She gets to the top of the hill, and that's where energy will get to be stored, which is called potential energy, which means you're not moving. Okay, and then she's going to move again, and she's going to have energy come out, and that is her still kinetic energy. So kinetic energy, you might have to put some energy in. You get to the point where you store the energy in potential, and then you let that energy out again in motion. Okay, so you have some different energy. So in this case, with our collisions, okay, I'm going to go back. A is going to swing into B, and B is then going to happen to move C across. So energy got transferred. A hit B, and B moves C. So potential energy is stored. Okay, things like your batteries, a spring in a watch, water in a dam. Okay, so and they have all different types of potential energy. So some are chemical, some are mechanical, things like that. Okay. A potential energy inside of a reaction depends on the atom, the number of bonds, and how they're arranged. So whether you're moving or not, the amount of energy never changes, only the type. That's a big thing. We need to understand that just like in the law of conservation of matter slash mass, you can't create or destroy matter. Same thing here. In energy, you cannot create or destroy it. You can only transfer it. Okay, you can only move it. So energy, like I said, is there's kinetic energy, the energy of motion. Okay, and here's our equation. Ke equals 1/2 mass times the velocity squared. Oh, that's supposed to point to mass. Velocity, they're a little off. Okay. So which has more kinetic energy, a slow moving school bus or a fast moving bullet? Okay, so here we're going to look at that thing. We see our bus and our bullet both go through kinetic. Okay, and here's the equation. So we have 1/2 and we have a lot of mass but a little speed versus a little mass and a lot of speed. Either may have more kinetic energy. It depends on the mass. Okay, and so we're going to look and see. And if you solve for them, you'll find out that the bullet has more kinetic energy because of its velocity. Okay. So when energy is released, it's called exothermic. So that's when you're going to feel heat, okay, when energy is released. When it's absorbed, it's going to be endothermic. It's going to feel cold. Okay, the energy required to raise the temperature of 1 gram of a substance by 1 degree is called its specific heat. And we're going to take a look at that more in our math calculations or the math of heat section or in lessons 4 and 5. Okay, some things that play a factor, your size, your temperature, the energy or heat that's already there. Okay, those are going to play factors into what type of heat we're also going to feel. If you already have heat in it, it'll probably be released. If you don't have heat in it, then you might need to put heat into it and then it's going to feel colder. Okay, so we have this thing called an energy diagram. You have on the y-axis going up and down the energy. And then across the x-axis or the bottom is the course of the reaction or the time. Okay. You have two parts. You have a reactant side, you have a product side, and then in this section where you have this hump right here, that's really important. The top of the hump, is your activated complex, okay? And then the gap between where your reactants start and the top of the hump is called your activation energy. It's the amount of energy required for your reaction to start. Some reactions require that you put energy in, okay? So that might be something like increasing the temperature, okay? We're putting it over fire. Some of it might be adding what's called a catalyst, which we're going to talk about in a little bit, okay? It may be making sure you have enough reactants. So things that you can affect your activation energy. And then once that happens, your reaction occurs and your products are made. So here we're going to see that this is actually an exothermic reaction. Okay, the reactants, okay, and your products and your energy are going to be on your product side. Okay, so energy is 10, which means you make 8 energy and then 2 energy as heat. Okay, in this case, your reactants will always be higher on the left side, and then your products will be lower on the right. Okay, so an exothermic reaction, reactants start high, products are low, because one of your products is heat, and that can't be recorded on this graph. Okay. Now, you can calculate that. You can subtract the energy of the reactants and the products. Okay. So you would subtract reactants from products. Okay. If you have an endothermic reaction, your reactants will start low, require, again, that energy to go in, but it's going to it's going to require a lot more energy. Okay. Then, after you get over that and the reaction happens, then you're going to have your products, and again, your activation energy, okay, right? You're going to see that it is, that you could add them together, and your products are going to be higher. If you have a positive change in heat, it's endothermic. If you have a negative change in heat, it's exothermic. And negative means that you've lost heat. That's why you feel it. Endo is positive because you're taking heat in and it's going to feel cold. I know that feels a little counterintuitive, but that's kind of how it works. Now, I said that we're going to look at catalysts. So catalysts affect how fast our reaction goes. We're going to look at this a little bit more in Unit 8. But what we can do is the first one is here. Here's our reaction. It requires some energy, okay? And then it makes our products. This is, again, an exothermic reaction. Now, I add my catalyst, and let's see what happens to a chemical reaction. Okay. So what's going to happen, and don't worry about that part up there, is what's going to happen is that this chemical reaction is going to be lower. So it's not going to require as much, which means the reaction will go faster. A catalyst makes the reaction go faster. And a great way to think about this is if you're at home, go put a cracker or a tiny piece of bread on your tongue and let it dissolve, okay? And then go find a piece of meat and do the same exact thing and time it, maybe like a minute or two, and see what happens. What's going to happen is that in your mouth you have a catalyst. I know, right? You didn't know that you had catalyst in your bodies. But yes, you have a catalyst in your mouth. It's called amylase. It is it's in your saliva. It is a biological catalyst, also known as an enzyme. I should have learned that in biology. And that catalyst, okay, only reacts with carbohydrates. So if you've done the experiment, you should have seen that your cracker or your piece of bread got really mushy, okay, but then your piece of meat, or you could even use cheese or something like that that doesn't have carbohydrates in it, stays the same texture because it's not breaking it down. So the catalyst will speed up the reaction, and in this case, the reaction is digestion. Okay, so again, no catalyst, and then for catalyzed reaction, the activation energy is lower. Okay, so catalyst lowers the activation energy of a reaction. Okay, so the kinetic energy and reaction rate, some factors. Okay, if you have lower temperature or higher temperature, different things like that, you can see the difference. So a lower temperature requires a little bit more energy, kinetic energy. Okay, so it goes a little bit quicker. Higher temperature made it slow down. Okay, okay, and we can see this here. Okay, in cold tea, many molecules have immediate kinetic energy. Okay, I'm sorry, yeah. And then in hot tea, there's fewer molecules that have very high kinetic energy towards the end. Okay, so you can kind of see the difference. So that's pretty much all we have for energy of reactions, and then we're going to talk a little bit more about them and heat through the next couple of lessons.